The next result, that is a theorem. Let f be a function from R1 to R1 for any r greater than 0, for any r greater than 0, let e suffix r be the set of all elements a in R such that a in R R1 such that the oscillation of f at the point A is greater than or equals to 1 by R. If this case is true, then ER is a closed set in R. We have to prove this. So suppose f is a real valued function from R1 to R1, and if for any positive real number r greater than 0, let we define ER be set of all elements in R such that the oscillation is greater than or equals to 1 by R. Then we have to prove that the set ER is closed. Now, if we assume that if X, so we have to prove that the set ER is closed. That is, we are going to show that the set is equals to its closure. It is, we are going to take one limit point of we are going to take a limit point of the set ER. Finally we will show that X belongs to, that limit point belongs to ER. There is nothing but ER is equals to its closure, that is, the set is closed. So that is what we are going to prove. If X is any arbitrary limit point, of the set ER, we shall prove that this X set belongs to the set ER. That is, when is an element belongs to ER, it is, we need to show that the oscillation of f at the point X must be greater than or equals to 1 by R. An element belongs to ER if it satisfies this condition. So now we are going to show that this X satisfies this condition. Then what happens is X belongs to ER and hence ER is closed. So now, to prove that ER is closed, we are going to show that the oscillation of f at the point X must be greater than or equals to 1 by R. Now, to prove this, it is enough to show that if J is any bounded open interval, J is any bounded open interval containing containing X, then the oscillation of F with respect to oscillation of f over j must be greater than or equals to 1 by r. Why we have to prove this one is, since the oscillation of f with respect to a point x is nothing but the GLB of all oscillations over j, where j is an open interval containing x. So now, if all the GLBs of this type, if we prove that it is greater than or equals to r, that is GLB means what? The greatest lower bound. Suppose this is a GLB. Okay. If this itself what? Greater than or equal to r, definitely so suppose this is omega of f colon semicolon x. This is nothing but GLB of all of them. See, GLB means there are infinitely many elements of the set comes very close to this GLB. There are infinitely many elements close to it. So by using the definition of GLB, if this is proved to be greater than or equal to 1 by r, then the GLB also will be equal to greater than or equals to 1 by r. So that many properties we studied in the earlier chapters, since this is equal to GLB of this. So now we are going to aim for this. We are going to consider an open interval j containing x such that the oscillation of f over j is greater than or equal to 1. Now we know a theorem. I put the symbol like this. If E is a subset of metric space M, I shall write this theorem itself. We are going to use it now. The star, I will put a symbol star. If E is a subset of metric space M, then x is element of M is a limit point of E, that is both necessary and sufficient condition if and only if every open ball, say about x contains at least one point of E. We are going to use this theorem now, this result. So I just am going to use it. I gave the reference. The symbol is star I use. So now the open interval j. Open interval in real line is nothing but open ball. So in bracket I write open ball. Open interval j must contain a point, say y in ER, because x is a limit point. X is a limit point of ER. That is what we have assumed. So as per so what is this? The result says if x is a limit point, then any open ball about that point should contain at least one point of the set E. So here in place of E, the set is what? ER, and x is the limit point. Therefore there must be an open interval j. This open interval j is an open interval, that is an open ball. Any open ball, whatever open ball you take, which about x should contain at least one point of E. So here the main thing is here this j all this J is varying. All this J contains X as the center. We can consider X as the center of the J. So this is an open interval containing X. So as per this theorem, it must contain at least a point Y of ER. So that is by star. So that Y, since J contains the limit point X of ER, and it is an open ball. So as per this theorem, it should contain J contains so this open ball should contain a point point Y of ER. But what is the oscillation of the function f with respect to J? This should be greater than or equals to the oscillation of f with respect to Y, because as per the definition of the oscillation of a function at a point A, because that is nothing but the GLB of all the oscillations of f over J. That is why this is greater than or equal to this. What is the relation between J and f? This Y is belonging to J, just now we proved, and also we proved that Y belongs to ER. If Y belongs to ER, the oscillation is greater than or equals to 1 by E. So that is what we have proved. To prove this, it is enough to show that if J is any open bounded interval containing X, then the oscillation of f over J is greater than or equals to 1 by R. If this is greater than or equals to 1 by R, then automatically this also must be greater than or equal to 1 by R, and that is what we wish to prove. So if this is greater than or equal to 1 by R, then ER is, if this is greater than or equal to 1 by R, then this X belongs to what? ER, where X is the limit point of this set ER. If it contains its own limit point, then the set ER is closed. So we proved that this is less than or equals to 1 by R. So this implies that the oscillation of f with respect to X is also what? Greater than or equals to 1 by R. This implies that X belongs to ER. So this implies that ER is the closed subset of R. Hence the theorem.